Hello and welcome to the live stream of Chemistry 223. I'm Travis. I'm a chemistry tutor at the Portland State Learning Center, and today I'm going to be talking to you a lot about Lewis bases and acids, as well as solubility, equilibrium, and complex ion equilibria as well. Just to get started, I'm going to post a few links in the chat window, like I always do. We've got links to the Learning Center's website as well as following them on Facebook and Instagram. Definitely check out those links as well. You can also check out the Portland State YouTube channel, and this is actually the playlist for this specific class, but you can follow that to their other YouTube channels as well. So definitely check back on there to follow past videos I've made for Chem 223, and you can also find playlists for Chem 221 and Chem 222 as well that I've done over the summer here if you need to review. So let's jump in and get started for today. So this first problem we have here is to write out an ionic equation for the dissolution of solubility product Ksp, and this solubility product Ksp expression for each of the following slightly soluble ionic compounds. So here there's 4 different ionic compounds here, and we just want to write out that balanced equilibrium expression as well as write the Ksp expression for those. This is a good thing we're going to do this a lot today on most of the problems. But starting out here, PbCl2 is going to start out as a solid, and it's going to dissociate into Pb, and it's going to be a 2+ aqueous plus Cl minus, and there's going to be 2 of those Cl's. Let me squeeze that 2 in. And that's also going to be aqueous. So I know this based off of the idea that we know that chloride is a -1 ion. It's always going to be negatively 1 charged. We can see that on our periodic table. If I jump over there and jump to my periodic table, chloride is group 17. So anything in this group here, all those halogens are going to be -1 charged when they're ionized. And therefore, if we look comparing that to lead, we have here 2 chlorides per every lead that we have. Therefore, that's going to make that lead a +2 charge. So we can see that's the basic dissociation equation and equilibrium that's going to happen when you put solid lead chloride or lead 2 chloride into water. The Ksp value, this is similar to basically all the equilibrium constants we've done, where it's basically the concentration of those products divided by the concentration of the reactants. And we always ignore solids and liquids when we talk about this. We're only looking for those aqueous ions that are in solution. And anytime you have something, basically have a stoichiometric ratio that's not 1, so in this case there's a coefficient there that's 2, we would take that to the 2nd power. Because really, I can write this mathematically. This is how I like to think about it, at least. I can write this like this. So when we're writing out the concentration of those ions, we end up writing the concentration of chloride twice. So it's multiplying by itself, which is why it's taken to that 2nd power. So when we do this concentration, it's really the concentration of lead, 2+, times the concentration of chloride squared. And that's going to be our solubility product expression for the Ksp value. Moving on to part B, we're going to take sulfur, sulfide, and we're going to say that that's an equilibrium. That's going to be a solid with 2 moles of silver. That's aqueous plus sulfur, which is aqueous. That sulfur is always going to be a 2-. It's right there on that periodic table below oxygen. There it is. Which means that it's always going to be, there's red, you can see maybe better. It's always going to be 2- when it's ionized. So in a similar way, this one, we have a similar type of deal where we have that Ksp value. It's going to be equal to the concentration of silver. And we're going to square that because the coefficient is 2 for the silver. And we're going to multiply that by the concentration of sulfur. And there's our Ksp value there. Part C, we're looking at strontium 3 PO4 2 is in equilibrium. It's a solid. I'm going to say it disassociates now into 3 strontium plus 2 PO4. Now to find out the charges for these, we can see strontium. Let's look at this periodic table. Is over here. It's group 2 metal, so it's always going to be a +2. So we can use that to say if this is going to be 2+, that means there's a total positive charge of 6. Since we have a neutral atom, this must be a 2-. That phosphate there. So the Ksp for this one, same as what we've been doing now, but now each one has a different coefficient. In this case, we take that to the 3rd power, and we'd multiply that by PO4 2- squared. And we get our basic solubility product expression. For part D, coming back with strontium, but it's SO4 for a sulfate. And that's going to be in equilibrium with SR. We said that's always going to be 2+. Those are aqueous. I left out my aqueous. My Gen Chem teacher would slap me for that. Or he'd slap me with a -1 or something. Plus SO4. This would be a -2 or 2-. I like to put the number first. Aqueous. So in that case, we had a 1-to-1 ratio between sulfate and strontium. So we'd have both of them to the 1st power, which means the Ksp is simply going to be the concentration of strontium 2+ ion times the concentration of the sulfate ion. And that's what we have for this first part. Now, like I said, we're going to be doing this a lot on all the different problems because all of them are going to deal with something like this. And that's going to be one of the first steps we do. So number 16 here, if we assume that there's no equilibria other than the dissolution are involved, calculate the concentration of all solute species in each of the following solutions of salts in contact with a solution containing a common ion. We want to show that the changes in the initial concentrations of the common ions can be neglected. So when we do this, one of the things we have to do is find out that Ksp value. We want to know what that is. And then we can use that to determine what our concentration ratio is going to be between, in this case for part A, thallium and chloride. So for part A, if I were to write out this expression, thallium chloride solid is going to be in equilibrium with or dissolution with thallium ions, which are going to be a +1 aqueous plus chloride items, which is a -1. I knew thallium had to be +1 because chloride was -1 and they had a 1-to-1 ratio. So that's our basic expression. The Ksp expression, just as we wrote before, is the concentration of thallium plus times the concentration of chloride minus. Pretty simple and straightforward in that regard. But how do we find what those are? We can see that those concentrations are really going to be equal to each other. And in this case, if we were to write out a rice table, something I went over last weekend, RICE, make a rice table for this. We already have the reaction, the initial, and I'm only going to worry about the ionic ones, the aqueous ones. The solutions don't really matter. Here we know this is going to be a +X. This is going to be a +X. Oops. Those are initial. Initial is always 0. Well, it is for in this case. And that means that at equilibrium, I'm going to have a concentration of X for both of those. So I can rewrite this expression as equaling x squared, because both the concentration of thallium ions and the concentration of chloride ions are equal to x. So now we just have to find out, well, what is this Ksp value? And we can find that by going to a table of solubility constants. And I use the one in the back of the book. That's Appendix J. I'm going to jump over to that guy there. Here you can see Appendix J. I've highlighted a few of the ones we're going to use today. And looking for thallium, TLCl is 1.7 times 10 to the negative 4. That's 1.7 times 10 to the negative 4. That's its Ksp value. Now we can, while we're in here, let's look for the one for part B. That's going to be a lead 2 iodide. So lead. This table is alphabetized by the name of it, which is kind of confusing to me. It took me a second to realize that lead is not going to be under P, it's under L. There it is. And we have, there we go, PBI2. I forgot to highlight that one. PBI2 highlighted. There we go. And that's Ksp is going to equal 1.4 times 10 to the negative 8. So hopping back to my page, I wrote down the Ksp values there for both of them. They're just up top here. And we can use those values then and plug in 1.7 times 10 to the negative 4 is equal to x squared. So now we have x squared there. We have to take the square root of both sides to solve for x. So that's x is equal to, I'm going to pull my trusty calculator out, make it a little bit smaller, and take the square root of 1.7 times 10 to the negative 4, and I'm going to say that's equal to 1.30 times 10 to the negative 2. Right there. So that's going to be my concentration in molarity of both of these two compounds, right? This is going to equal the concentration of thallium ion, and it's going to equal the concentration of chloride ion. Since they have that 1-to-1 ratio, they're both equal to x. So we solved for x. Now, the second part of this question is to talk about show that the changes in the initial condition or concentrations of the common ions can be neglected. In this case, it's in 1.25 molar of HCl. So one way we can do that is take the concentration we have and divide it by that 1.25 molar. This should be molarity, and see what that's equal to. Pulling my calculator back up, I can see I grab this value and just divide by 1.25. I'm going to actually multiply that by 100 too. I'll get it into a percentage is the idea. And we can see just about 1%. 1.04%. So that's a really small percentage. Anything less than 5% or so we can say is basically negligible in that case. So the solubility has basically not changed there. For part B, now write the equation out again. That's PBI2 solid, just disassociating into PB2 plus, that's going to be aqueous, plus I2, or I minus, and there's going to be 2 of those. Let me space that out so it's a little easier to read. There we are. So since we had I2, there's going to be 2 moles of iodine, or iodine, floating around in there. Iodide, there it is. And that's going to be aqueous as well. So my Ksp value for this is going to equal the concentration of PB2 plus times the concentration of I minus squared. And we square it because of that stoichiometric coefficient. Now, the Ksp for this we know is 1.4 times 10 to the negative 8. And we can do our Rice table here just the same. These get pretty simple to do once you get the idea of how to do them. We already have our equation, and initials are 0. Really, we're looking at what that change is. That change is going to be x and 2x. So we're going to end up with an x and a 2x here. So plugging these values in now, we can see our Ksp is equal to the concentration of lead 2+, which is going to be x, times the concentration of iodide squared. So the concentration of iodide is 2x. We're going to square that. So you see it's a little different when you start to get a lot more complicated in a certain way. Because now we end up with a Ksp equal to 4x squared. Or sorry, x cubed even. Because it's this x times x squared is x cubed, and this 2 gets squared. That's something that's easy to forget. People forget to square that 2. So by squaring that 2, we get 4. So it's 4x cubed is now going to be equal to our Ksp value. Remember, our Ksp is 1.4 times 10 to the negative 8. So now we just have to solve for x. And this comes down to a little bit of algebra that we have to do. I'm going to divide each side by 4. 1.4 times 10 to the negative 8 divided by 4. And then I'm going to take the cubed root of that to equal x. So let's plug that into our calculator here. Now, to get the cubed root, I have to hit the math button on my calculator and find this value here with little 3 next to the square root value and hit that. That gives me a cubed root. And then I can type in 1.4 e to the negative 8. I'm going to divide that by 4. And make sure that's all under my square root bracket. Sometimes it'll give you parentheses. Make sure it's open and closing the parentheses around the entire thing, because we want to take the cubed root of that whole fraction. And that's going to lead me to 1.5, 2 times 10 to the negative 3. That's going to be the molarity, and that's going to equal x. So that equals concentration of lead 2+ is equal to x, which is equal to 1.52 times 10 to the negative 3 molar. But the concentration of iodide is going to be equal to 2x. So that's going to be equal to double that. So I can just hit times 2. I get 3.04 times 10 to the negative 3 molar. So those are my concentrations for this problem here. Now, we had this in a solution of a different common ion, right? Calcium iodide, right? Calcium's 2+, iodine's -1. We have 2 of those floating around. And the idea here is we want to see, well, what is that concentration difference? What is this concentration of iodide going to do to my constant value? In this case, for every molar of calcium iodide we have 2 molars of iodine floating in there. So from that calcium iodide, we can say that the iodide concentration is going to be equal to 2 times 0.0355 molar. Which is equal to 0.0710 molar. So I needed to find that, because then I'm going to do the same thing as what I did over here. I have that. I'm going to take the concentration of iodine here, which is 3.04 times 10 to the negative 3. I'm going to divide that by that 0.0710 molar. Multiply by 100 to figure out what percentage of that is going to be, and see if it's anything relatively significant. So I take the same number I had here. I'm going to then just divide by this number here. It's nice when everything's in your calculator, and multiply by 100. That's going to equal 4.3%. So 4% is really not very significant. I said earlier, anything under 5% is basically negligible in that regard. This is approaching that 5% limit, but it's not quite there. So I'd still say that concentration change doesn't really matter. This next one, I've redacted a few of the questions just because, well, part A is something we basically did here in part A, and some of the other ones I was just trying to save a little bit of time on. I wanted to focus on C and D because they're a little bit more complicated than the others. But again, it's a very similar idea. So if we assuming that no equilibria other than the dissolution are involved, calculate the concentration of ions in a saturated solution of each of the following, looking at Appendix J for the solubility products. So part C here, I'm going to write out the equation. Ag2, that's silver 2 chromate, solid, in equilibrium with be 2 silver ions, they're aqueous, plus chromate, 2 minus. There we go. So in this case, we want to also go back and look up what these Ksp values are. So I'm going to switch back to there it is, my table here, and I'm going to look for silver. There we are, silver chromate. Nope, that's not the right one. It's the one below it. There at a 9 times 10 to the negative 12. So I'm going to write that here. 9.0 times 10 to the negative 12 is my Ksp. And we are going to also look up while we're here this calcium C2O4 with H2O. Maybe up a little higher. I highlighted that one already. That's going to be 1.96 times 10 to the negative 8 equal my Ksp. So now that I got my Ksp values, switch back to my iPad. I wrote them there next to the problem. I can then go ahead and try to work on solving this in this case. So we want to calculate the concentrations of the ions in a saturated solution for each of those, for each of these compounds. To do that, we want to find out that Ksp, in this case, the expression that we need to write is Ag plus squared times chromate 4 2 minus, not chromate 4, but CrO4 to the first power. So we can do our rice table. Move that off to the side a little bit. And initial, change, and equilibrium are up there. There's my reaction equation. The initial is 0 before anything's dissociated. The change is going to be a plus 2x and a plus x. So I always say 1 is x, and whatever that stoichiometric ratio goes up is going to be my multiple, therefore, of x. At equilibrium, I'm going to have a 2x and an x there. And now I have a Ksp value. And I can write this as with my Ksp 9.0 times 10 to the negative 12 is equal to my concentration of silver, which is 2x squared, times the concentration of chromate, which is going to be just x. Doing the math here, 2 times 2 is 4, so that's going to be 4x cubed, which is equal to my 9.0 times 10 to the negative 12. Solving for x, I take each side, 9.0 times 10 to the negative 12, divide by 4, and then take the cubed root to get x. Just a little bit of algebraic manipulation to solve for my x variable. And now I can go ahead and plug that into my calculator. It's going to be the math button, hit the 3, or the cubed root, 9.0 e to the negative 12 divided by 4 is equal to 1.31 times 10 to the negative 4. And see that's going to equal the concentration of CrO4, 2 plus, 2 minus. But to get the concentration of silver, I need to multiply that by 2. So I take that value times 2. I get 2.62 times 10 to the negative 4. So that's the concentration of silver plus equal 2x, which is equal to 2.62 times 10 to -4 molar. And there's my answer, a weirdly circled boxed manner. So that's my basic process on how to get these here. I'm going to run through the next one just really quick. I'm going to make a little bit of extra room. Nice thing about working on a tablet. For part D. So for part D, I'm looking at this calcium C2O4. So that's going to be CaC2O4 solid dissolving into with H2O. Forgot my H2O, or hydrate. I'm just going to say Ca2 plus aqueous plus C2O4 2 minus aqueous, and you can say plus H2O liquid. So when I do my rice table, we can see the initial for all of these is 0. Essentially, this one doesn't count. It's liquid. We're not going to be worried about that. We're really just worried about the concentrations of those aqueous solutions. So the initial is going to be 0 for those. The change in that is going to be a plus X and a plus X, because it's a 1-to-1 ratio really between them. So at the end of the day, it's X and X. So our Ksp is really going to equal that concentration of Ca 2 plus times the concentration of C2O4 2 minus. They're both to the first power, so that Ksp is equal to X squared. And we see our Ksp value here at 1.96 times 10 to the -8. So that's 1.96 times 10 to the -8 is going to be equal to my X squared. Taking the square root of everything, we'll get X. 1.96 e to the -8. Oh, take the square root of that. Answer. That's going to be 1.40 times 10 to the -4 is equal to X. So in that case, this is equal to the concentration of calcium 2 plus and my C2O4 2 minus. It's equal to both of those because they have the same concentration once they're dissolved. So that's part C and D of number 26. Let's move along to number 28. Again, just to save on time, I have taken out the first two, and I'm just going to do the bottom three. They're a little bit more complicated, so I wanted to cover those. So here the following compounds are found in mixtures of ions in equilibrium with slightly soluble solids. From the concentrations given, calculate the Ksp for each of the slightly soluble solids indicated. So again, the Ksp is going to basically equal the concentration of the products divided by the concentration of the reactants. And we always ignore the reactants or the products if it's a solid or if it's a liquid. So in most of these dissolution statements or expressions, we're ending up with just the concentration of the ionized product. So for part C, we have this equation here, PbF2 solid is going to dissociate into the concentrate, Pb2 plus aqueous plus, let's say 2F minus aqueous. So again, we got to make sure that ratio is the same once it dissociates. F2 is not going to stay in as an ion in solution. It's going to split up and become two different F minus ions. And then this is what we end up having. The Ksp value for this is going to equal the concentration of Pb 2 plus times the concentration of F minus squared. And here they're giving us these concentrations. We have to just calculate what that Ksp is. So in calculating that, the Ksp is going to equal 2.1 times 10 to the negative 3 multiplied by 4.2 times 10 to the negative 3 squared. So we're squaring the whole concentration of the fluoride ion in that regard. And then plugging in to our calculator, we get 2.1 times 10 to the negative 3 times, I'm going to put parentheses here, 4.2 times 10 to negative 3, and then I can close my parentheses and square that whole parentheses, which gives me Ksp value equal to 3.7 times 10 to the negative 8. So once you get good at writing down the balanced equilibrium equation and then writing a Ksp value from that, if you have the concentrations, you can find that Ksp value just by doing the math of it. But the key is to make sure you get that expression down right for the Ksp expression. So for part D, taking Ag2 CrO4 solid, it's going to be in equilibrium with Ag plus. 2 of those, there's 2 moles of Ag plus the tried to move it over and it doesn't quite work. So 2 moles of Ag plus the concentration, or sorry, plus CrO4, jumping ahead of myself, this would be a 2 minus. And they're both aqueous. Okay. So my Ksp value is going to equal the concentration of silver ions squared times the concentration of chromate to the first power. Using the concentrations they give me up here, these are the concentrations at equilibrium. We can determine what that Ksp is. So Ksp would be equal to 5.3 times 10 to the negative 5, the concentration of silver, which squaring that, times 3.2 times 10 to the negative 3. So plugging that into my calculator, I'm going to put parentheses 5.3 times 10 to the negative 5 squared times 3.2 times 10 to the negative 3. And this is going to be Ksp equal to 9.0 times 10 to the negative 12. And this guy might even look a little familiar to be, yep. Yeah, look, we used that in the last one. We had to look that up on the table last time. We didn't have those concentrations. But our answers match, which means we did a good job. So there's our Ksp of part D. Part E is indium trifluoride. Solid. So dissociate into Im3 plus aqueous plus 3 fluoride ions. So my Ksp is going to be equal then to the concentration of indium times the concentration of fluoride to the third power. And this is going to be equal, so Ksp is equal to 2.3 times 10 to the negative 3. That's what they tell me that is. And then the fluoride is 7.0 times 10 to the negative 3. I'm going to take that all to the third power. So that should have been a 2.3. I missed the 2 somehow. 2.3 times 10 e to the negative 10. Well, I was way off. Okay. To negative 3. That's better. Times 7.0 times 10 to negative 3. Forgot my parenthesis. There we go. I'm going to take that all to the power of 3. This is going to give me a Ksp, which is equal to 7.9 times 10 to the negative 10. There we are. There's my Ksp for part D. Or part E, even. So number 32 is my next one. I'm going to calculate the concentration of thallium ion when thallium chloride just begins to precipitate from solution. That is 0.025 molar in chloride. So when it just starts to precipitate from the solution, that means the Ksp value has just been reached. The concentration combinations of thallium and chloride are high enough, or at the right level, to just barely start to precipitate. So it's just crossing that brink, essentially. We can never really get exact. You're always a little bit before, a little bit after, and things are always kind of fluctuating in there. Remember, this is talking about the rate of the dissociation is just the same as the rate of the precipitation. So they're really going back and forth on different rates, and when those rates equal each other, we get this saturation, essentially, where we're actually at, we actually get the precipitation of things. Maybe not saturation, but it starts to precipitate because we've reached the solubility level of everything. So in this case, the Ksp for this, we said earlier, is equal to 1.7 times 10 to negative 4. And that was over in part, the first one we did here. Nope, maybe not the first one, the second one. That was from right here. 1.7 times 10 to the negative 4. So knowing that, and we know that this is going to be equal to the concentration of thallium ion times its concentration of chloride ion. And they're saying at this level where it just starts to precipitate, we have this concentration of chloride. So what we can do is rearrange this equation to find out what that calculation or the concentration of thallium ion is, just by plugging in this value of chloride and using that Ksp value, because then we know the concentration of thallium must be found with that expression. So we can do that by dividing each one, so it's 1.7 times 10 to the negative 4, by the concentration of chloride, which is in this case 0.0250. And that will equal the concentration of thallium ion. So if I plug that in, that's 1.7 times 10 to the negative 4. We're going to divide that by 0.025, which is equal to 6.8 times 10 to negative 3. That's going to be that's the molar concentration of thallium at that point. So that one's pretty quick and easy. Let's look at number 38. Number 38, something fairly similar. We want to know what is the concentration of silver ion, or how much a silver ion concentration is required to reduce this CO3 ion to 8.2 times 10 to the negative 4 molar by precipitation of Ag2CO3. So I like to write out the equation. I'm going to do it for this one. Ag2CO3. I know we did it on a previous one, but just to understand what's happening, we have that solid compound dissociating into Ag plus aqueous plus CO3 2 minus. I don't know why I put the concentration bars on there. Let's write that a little neater. Okay. There we go. So that's our basic dissociative equation. The Ksp value for this is going to be equal to, and I had to look this one up again. This is slightly different than the one we did before. This is, oh, silver. There it is. There we are. So that was this top one up here. We looked at silver chromate down below. This is carbonate. And that's going to be the 8.1 times 10 to the negative 12. There we go. So now that we have that Ksp value, we also should recognize that that's equal to the concentration of silver ions squared times the concentration of carbonate. So if we were to do a rice table for this, actually I don't know, we don't need to, because we have Ksp and we have the concentration of carbonate right there, 8.2 times 10 to the negative 4. So really we just have to solve for that silver ion concentration. So working with just the expression to begin with, I'm going to rearrange that expression algebraically to solve for the silver ion. First, I'm going to divide each side by the concentration of concentration of carbonate. That's CO3 2 minus, which is going to equal the concentration of silver squared. Taking the square root of each side, and the square root here basically loses that square, we get our concentration of silver solution or expression. Now we just have to plug in those values. So we said Ksp is 8.1 times 10 to the negative 12. We're going to divide that by this 8.2 times 10 to the negative 4. And we're going to take the square root of that to find Ag plus. So it's 8.1 times 10 to the negative 12 divided by, parenthesis, 8.2 times 10 to the negative 4. And I'm going to take the square root of my answer. So that is equal 9.94 times 10 to the negative 5. It's really 9.9 to keep my sig figs proper. The concentration of Ag plus. And that's what they were looking for there. Number 69, using the dissociation constant Kd or Kd that's equal to 3.4 times 10 to the negative 15. Calculate the equilibrium concentrations of zinc plus 2 and hydroxide in a 0.0465 molar solution of zinc tetrahydroxide, or zinc 2 hydroxide. So for this one, write out my expression here with the zinc hydroxide is, actually it's aqueous even, because it's a solution in this case. So now we're getting into more complex ion formations. Zinc 2 plus aqueous plus 4 hydroxide aqueous. So that's going to be the basic equation that we're going to work with, and we're going to break that down with a rice table. So the initial concentrations of all of these we know. So we start off with 0.0465. molar, and we have no ions yet present before it starts to dissociate. The change in that, we're going to say it's going to be a minus x, an x, a plus x, and a plus 4x. And at equilibrium, I have 0.0465 molar minus x. And then here I have plus x, or just x, and 4x. Now our Ksp expression for this, as I said earlier, is the concentration of the products, in this case zinc 2 plus times the concentration of hydroxide to the 4th power divided by the concentration of zinc hydroxide. So we can break this out and do the quadratic equation, but there's a way to assume, since we have such a large KD value, or it's really small, really, it's 10 to the negative 15, I can assume that x is much, much smaller than 0.1. So it's a really small number. So I can basically say that this change in molarity of our ionic solution is negligible. And in doing that, it simplifies this whole equation, because now I can write this Ksp is equal to x, which is the concentration of zinc, times 4x to the 4th power divided by 0.0465. So now we can simplify that a little bit. 4 to the 4th power, that's 4 to the power of 4 is 265. That's 265 times x to the 5th power divided by 0.0465. I wrote Ksp this whole time. Yep. I should be writing Kd. My mistake. So that Kd value is equal to 3.4 times 10 to the negative 15. So since we know that Kd value, we can then just solve for x in this case. We can multiply each side by the denominator there, leaving us with 265 x to the 5th is equal to 3.4 times 10 to the negative 15. And we're going to be multiplying that by that 0.0465. And what we're trying to do is isolate x, so I'm going to just divide each side by this 265. And now I just need to take the 5th root of this value. So I'm going to find that value first, so it doesn't get too complex on my calculator. That's 3.4 e to the negative 15 times 0.0465. Divide that by 265, and I get this x to the 5th is equal to 5.97 times 10 to the negative 19. And then I want to take the 5th root. So in my calculator, how I do that is I hit the 5 first, go to math, and here I'm looking for this square root with the x next to it. So it takes whatever value I had in the calculator and it puts that up for that root. So I'm taking the 5th root in this case of the value I just found, which is equal to 2.3 times 10 to the negative 4. Put a little 5 there, put a 5 there, show my work. So now I've found the value of x, and that relates to the concentration of zinc, 2 plus, is equal to x, which is equal to 2.3 times 10 to the negative 4. So that's the concentration of zinc. Now the concentration of hydroxide, however, that's equal to 4x. So we have to multiply the value we got for x by 4. Get 9.1 times 10 to the 4 to the negative 4. That's molar. And we still want to know what is the concentration of the zinc solution, zinc tetraoxide. So that ZnOH4. Now we said that this change is going to be relatively negligible. So let's see how right we were, or wrong we might have been. Because that's supposed to equal 0.0465 molar minus X. So if I take 0.465 minus this value, I get this is equal to, and move that decimal over 2 places, 0.456. So it was very small, pretty much negligible, but not quite. There was a little bit of a change there, essentially. If we were to include that in our calculation, it just gets to be a much harder calculation to make, because you don't really even have a quadratic here. You'd end up with x to the 6th power, which gets a lot harder to solve, essentially. But your answer is going to end up coming up something all very close to this value. Either way. There's our concentrations for all of those values. Number 71 here. I think this is the last one I'm doing. Yeah. So using the dissociation constant, Kd is equal to 10 to the negative 44. Calculate the equilibrium constants or concentrations of iron 3 and cyanide in a solution of 0.333 molar solution of iron hexacyanide. So same idea as what we did before. I'm going to write the equation for it. We're going to plug it into a rice table. So aqueous is in equilibrium with iron. Now, this tells me it's 3+, but I can also figure that out based on the charge. Cyanide's always a -1, so it's a -6 ions. We know the whole compound needs to be -3, which leaves iron to be a +3. And it's going to be aqueous plus 6 cyanide. Aqueous. So when we do our rice here, initial change and equilibrium, we can see the initial concentration here is 0.333 molar. I always want to leave out a 3. And our initial for these two is 0. The change can be a minus x, minus x, minus 6x. And at equilibrium, we're going to have 0.333 minus x. Here we're going to have just, oh sorry, this is a plus and that's a plus. We are adding on the product side. So that's x and a 6x. So writing out my Kd, which would be equal to, in this case, 10 to the negative 44, which needs to equal x times 6x. Well, I'm jumping ahead of myself, aren't I? Let's start out here. The expression is the concentration of iron 3+ times the concentration of cyanide to the 6th power. I'm going to divide that by concentration of FeCN6, 3 minus. That's going to be the expression we're going to be working off of. Plugging in these values from our rice table, we can see that Kd is equal to x times 6x to the power of 6 divided by 0.333. And again, we have a really small Kd, so I'm going to say this x is negligible. And that also makes our equation a lot simpler to solve, because otherwise you end up with, a polynomial to the 7th power, to the 7th order that you're trying to solve, which becomes a lot more difficult. So now we can plug in, this is equal to 10 to the negative 44, which is a really, really, really small number. And we could solve. So multiplying each side by the denominator there, and taking 6. So I'm just going to say, ignore my calculator for a second. I'm going to say that's 6 to the 6th power times x to the 7th power is going to equal 10 to the negative 44 times 0.333. I can divide each side by 6 to the 6th power. 10 to the negative 44 times 0.333 divided by 6 to the 6th power. Taking the 7th root of that, big 7 there, it goes all the way down with the 7 there. Taking the 7th root of both sides, then to solve for x. Jumping over here, now I'm going to do this on my calculator, I'm going to hit a 7, and then I'm going to hit the math, and hit that x to the root. So I have the 7th root, and then I can plug in at 10 to the power of negative 44, and I'm going to multiply that by 0.333. Divide that by 6 to the power of 6. That's going to be equal to 9.5 times 10 to the negative 8. That's my value for x. So 9.5 times 10 to the negative 8, we can really see here that my concentration of Fe cyanide, hexacyanide, which should be equal to 0.333 minus this, I'll just say x for lack of a better word. I can do that, 0.333 minus that value, still basically 0.333. So in this case, that x was truly negligible in there. There's completely insignificant to the calculation for what we were doing. In this last problem, it was negligible but not insignificant. There was a slight change in the concentration based on what the sig figs that we had here. In this case, the sig figs was 3 decimal places out, 3 sig figs, and by subtracting away the change in that, we end up with a very negligible number. Or not even negligible, but insignificant number. It gets lost in the sig figs. For the concentration of iron, 3 plus, we can see that's just equal to x, which is going to be equal to that 9.6 times 10 to the negative 8. For the concentration of cyanide, that's going to equal 6x. So this equals this value here times 6. It's going to be 5.7 times 10 to the negative 7. And there is all of our concentrations. They're all molarity. And we're able to calculate all of those concentrations after the equilibrium has been reached. That's all I have for you today. I do have drop-in tutoring hours right now after this. I'm going to jump straight into the Pingy room. So if anybody is out there and has any questions for me, definitely just drop in, ask questions. If it could cover Chem 221, 222, 223, or anything else for that matter, I'm happy to talk you through things. Again, my name is Travis. You can also schedule a drop-in appointment with our chemistry tutor Amir through the Pingy app. So log in through there, and he's available through the week as well. Have a great day, and I will see you again on Tuesday.